On November 19th in the year 2012, a gathering of the greatest minds of the universe convened to observe the great conjuncture between Sagittarius A, the massive black hole at the center of our galaxy, and our Sun. Using two independent, highly advanced telescopic systems, one located on Mars, the other, Ganymede, the largest of Jupiter's orbiting moons, the stage was set for the black hole wars to resume. Theorists prepared for this great intellectual battle over their understanding of the nature of black holes. This battle would be held at the Great Gedanken Games and would be televised via satellite feed at Gedanken Stadium, streaming live over the internet. Bypassing the great distance from our solar system to the center of our galaxy, after having undergone cryogenic sleep for a very long time, the intellectual audience, theoretical observers, and volunteer subject were all in position, ready to begin.
Welcome everyone to the Great Gedanken Games. What an exciting lineup of thought experiments we have for you tonight. Afternoon, morning, depending on what time zone of which planet you're on.
That's right, Phil. And who would have anticipated tonight's main experiment?
Well, apparently, Sophie, some mild-mannered philosopher from California Earth has placed a challenge to top theoretical physicists regarding black hole theory, claiming that he can upset current theories with what he calls the Susskind-Hawking paradox.
Located at the Mars Observatory, physicist Stephen Hawking awaits results from various tests regarding his theory of black hole radiation.
I want to understand the universe and answer the big questions. That is what keeps me going.
Located at the Ganymede Observatory, physicists Leonard Susskind and Harold T. Hooft await results from various tests regarding their theories of black hole complementarity.
This is all preliminary to the black hole war.
You ain't seen nothing yet.
Approaching the center of the galaxy, we find our volunteer subject, philosopher Gavin Wince, as he prepares his highly advanced Cobalt-1 hyperspace shuttle to conduct the main experiment of the Great Gedanken Games. Before we get started, let's see what led up to tonight's main event.
A black hole begins with a momentous event: the death of a star. As a massive star dies, it collapses in on itself. Where the star had been, gravity now becomes infinitely powerful, and anything which approaches it is sucked in. At the invisible heart of the black hole is a mysterious place where the fabric of time and space are transformed, and the equations of physics break down. This single point is infinitely small and infinitely dense. The center of a black hole bears a startling resemblance to the beginning of the Big Bang. Which is why Hawking was convinced black holes would help him reach a deeper understanding about the nature of the universe.
Black holes are places where space and time come to an end, and matter is crushed out of existence. If we could understand how time comes to an end in black holes, it might help us understand how time began in the Big Bang.
He wanted a complete mathematical description of a black hole. It was an extraordinarily difficult task. Until Hawking, it had been assumed that black holes were dark, cold places that lasted forever. But Hawking suggested in effect that the black hole was radiating heat and burning up. That had important consequences. Hawking was saying that a black hole would eventually disappear, and it was this that caused the problem. Throughout its life, a black hole would suck in anything that came near it, from astronauts to light. But when the black hole was gone, what happened to all that stuff? Hawking claimed it just disappeared too. But scientists hated this idea, for it wasn't just inconvenient, it was scientific heresy. According to physicists, everything in the universe is made up of particles. It's long been one of their most deeply held beliefs that the information encoded in these particles can never be lost.
Scientists usually assume there is a unique correspondence between the past and the future, cause and effect. But if information is lost, this is not the case.
Once you admit that information can be lost, you can't quarantine it and say it only happens in black holes. You're going to find it happening in all kinds of contexts.
It wasn't until 1972 that astronomers were actually able to see a black hole. Had there been only one, then perhaps physics could have found a way around the information paradox. It could have become a unique exception. But there wasn't just one black hole. Soon astronomers had found thousands. Then there were millions. Astronomers found an enormous supermassive black hole at the center of our galaxy. If the information paradox was true, then all of these black holes were machines eating up information. And so across the world, physicists were increasingly keen to solve it. No one more so than Leonard Susskind. The man who had come to understand the disturbing implications of Hawking's work and become his chief opponent.
This was something that violated all of the principles of physics, everything that we knew about physics up to that point.
Leonard Susskind got very upset. I think he was the only one in the room who fully appreciated the implications of what I had said.
This concerned an inexplicable contradiction that seemed to occur at the edge of the black hole. The event horizon.
As that person gets closer and closer to the black hole, they will be evaporated, ionized. All the terrible things that would happen from extremely high temperatures would happen to them, and eventually would just be converted to electrons, protons, neutrons, just completely destroyed. The really bizarre thing is that the same laws of nature tell you that from the perspective of somebody falling into the black hole, they would see nothing special at the horizon. They would just freely fall through it, no hot temperatures, no destructive influences, and would cleanly pass through the horizon with absolutely nothing interesting happening. While it seems extremely weird that both of these stories could be true, as far as we can tell now, both stories are true.
What Susskind said is that as the person went into the black hole, the information contained in their body was smeared on the event horizon, so they'd appear to outsiders to disintegrate. But the person themselves would still think they were intact.
If you looked in incredible detail, far more detail than we can really imagine, at everything taking place on the surface of the black hole, we could reconstruct everything taking place inside.
And that means information is not destroyed. It's all, theoretically, able to be retrieved. The information paradox, according to Susskind, was solved. A paper emerged which vindicated Susskind.
This was enough to pretty much convince most of the community of physicists that information could never be lost from a black hole.
After reviewing all the recent material on the information paradox, Hawking decided to tackle directly the paper which had convinced people Susskind was right, and he was wrong. But this time, as he contemplated it, he felt he could see something new. For the first time in 30 years, he could see a fresh way to consider the black hole's greatest puzzle, the information paradox.
I want to report that I think I have solved a major problem in theoretical physics that has been around since 30 years ago.
Hawking claimed Susskind wasn't right either, and instead he now had his own solution. In effect, those universes where black holes existed would be cancelled out by those where they didn't. And that meant information didn't disappear, because there would be no black hole for it to become trapped in the first place.
If one waits long enough, only the histories without a black hole will be significant. So in the end, information is preserved.
His paper struck many as big on claims, but short on maths.
A black hole is a place where nothing can get out of, but things can fall into it. And if things can fall into it and they can't get out, they're gone. But then the black hole evaporates. Stephen had proven that beyond anybody's doubt. And so things fall into the black hole, they can't get out, the black hole evaporates, poof, it's gone. Some of us, particularly Gerard and myself, very, very strongly felt that this really undermined everything that we knew about physics. Information means distinctions between things. And it was a very, very basic principle of physics that distinctions never disappear. And Stephen was saying exactly the opposite.
It was a very fundamental problem. And the way I always saw it is Hawking was using quantum mechanics, in particular quantized fields, to derive his result. From that, it was derived that there was information, and there was information disappearing. Well, the fact that information disappears is at odds with quantum theory itself. So he uses quantum theory to derive a result which basically was at odds with quantum theory. What he did was by itself mathematically correct, and nobody doubts that. But the final result had something in it that couldn't be true. And so this is what in physics we call a paradox. As soon as you encounter a situation of this sort in the physical world, we are very happy actually. If there's a paradox, it means there's work for us to do, we have to clear this thing up. And if you look at the past, you know quite well that when people start to clear up paradoxes, new discoveries are being made. And that's why we're also excited about this thing. There's something wrong, the derivation itself seems to be flawless, but there's something wrong anyhow with the result.
Conflict of principles. And if anything can break the impasses in physics, if there are no experiments available, it's conflicts of principle. When conflicts of principle arise, that's when major new paradigms can shift.
That's the excitement.
Whoa!
Boy, can I feel the tension in the ether from here. And there even isn't any ether either.
Funny, huh? That's pretty intense, Sophie. How did they figure out who would be the volunteer subject?
That both Gerard and myself reacted to almost violently, intellectually violently. We weren't going to throw Stephen out of his wheelchair. Oh, you like that? Both of these stories involve throwing somebody, a philosopher, into a black hole.
All right, fine. I'm not too chicken to...
I've studied black holes in all sorts of ways and found that they are extremely dangerous objects. You want to stay away from them. If you ever would come close, you'll be torn to pieces long before you can enter into one. And if you could enter into one, you would certainly not re-emerge out of another black hole. You'll be lost forever.
Okay, and with that, let's get started.
Apparently, we're all in for a big surprise. Wince has not yet revealed what he calls the Hawking-Susskind paradox, nor how he intends to create his upset in the physics community.
Wait, look!
I think Wince is rolling out his thought experiment as we speak.
Oh no, not the CP violator!
Apparently Wince intends to conduct the well-known CP violation experiment using the asymmetrical decay of supercooled cobalt-60 in a magnetic field, all within a black hole? Is this guy nuts? What does he expect to accomplish? The information paradox is here again, inside black holes. In 1956, The Wu experiment was conducted to check the parity conservation law of beta decay using isotope cobalt-60 at a supercooled temperature to slow down the beta decay radiation such that it could be measured. However, it was discovered that beta decay radiated more towards the north pole of a magnet than towards the south pole, indicating that matter particles spin more in one direction than the other. An unexpected discovery of parity violation. With more elaborate experiments, it was shown that charge symmetry was also broken. These broken symmetries became known as charge parity violations, or CP violations for short. Let physicist Richard Feynman discuss the implications of this discovery.
There's a deep connection between the symmetry principles and the conservation laws. Certain experiments indicated that they got produced all kinds of puzzles. I won't go into detail. We got into tighter and tighter difficulties, more and more paradoxical situation, until somebody proposed, Li and Yang proposed, maybe the principle that right and left symmetry, that nature is the same for right and left, is not right. That when we have a radioactive disintegration, which, for example, this is a neutron disintegrating into a proton, electron, and an antineutrino. The thing that's interesting is that if you measure the spin, electrons are spinning as they come out. If you measure the spin, you find out that they're spinning to the left. And thus, the law of this, that world was symmetrical for left and right, has collapsed. It's extremely interesting that there seems to be a deep connection between the conservation laws and the symmetry laws. People have called it the parity, and they have a conservation law called the conservation of parity, but those are just complicated words in the case of the quantum mechanics. All we're saying is that the right and left symmetry law is not valid. Now the question is whether the matter works the same as the antimatter. And it was believed that this is true, that matter and antimatter have the same laws. Now the next question is this. If I look at this integration but with antimatter, does the antimatter behave like the matter in the sense that it comes out left-hand thread, or does it behave the other way? The remarkable feature of this effect that we can distinguish right and left is that we can distinguish right and left only with a very weak effect, with this beta disintegration. What it means that nature is 99.99 indistinguishable right from left, but that there's just one little piece, one little characteristic phenomenon which is completely different in the sense that it's absolutely lopsided, is a mystery that no one has the slightest idea about yet.
Here is how my thought experiment works. In this spacecraft, we will duplicate the Wu experiment using the asymmetrical beta decay to send light signals outside the craft at a fixed pulse. A CP violation atomic clock, so to speak. Remember, in this experiment, the parity violations can only be detected at supercool temperatures. The slightest increase in temperature destroys the parity violation data. Though the equivalence principle does not allow us to feel when we have crossed the event horizon, we should see the effect the event horizon has on light. According to physicists at the University of Colorado, we would see the intake of light, the path we traveled into the black hole, and the outflow of Hawking radiation merge. Therefore, just before we see this effect, while still slightly outside the event horizon, as far as the outside observers can tell, we will then start up the CP violator so that the charge parity violations start statistically at the event horizon and continue on inside the black hole, no longer visible to outside observers. Therefore, the information regarding the asymmetry found in the charge parity violations in our experiment is cut off from the outside world. Herein lies the problem. Though black hole complementarity is a viable solution to the black hole information paradox, and though Hawking's sum over history solution might be equally viable, neither theory take into account this kind of charge parity violation. The broken symmetries found experimentally in the weak force interactions is a wrecking ball, not only to both Hawking and Susskind's position, but also to theoretical physics as a whole. Since the spaceship conducting the CP violation experiment is falling into the black hole, The outside observer would see the spaceship disintegrate before it can display parity violations, given that the heat of the event horizon would prevent the spacecraft from being cool enough to conduct the experiment as designed. The parity violations occur inside the black hole, do not show up in the information surrounding the horizon. The heat of the particles would cancel out the probabilities for charge parity violations, and the outside experimenters would see charge parity's symmetry preserved as the disintegrated ship radiates away. In other words, symmetry information observed outside, asymmetry information observed inside. Susskind pointed out
that distinctions never disappear, that they may get scrambled, that they may get all mixed up, but if you start with one configuration and you let it go, or you start with a different configuration which has different information and you let it go, they'll stay different. And Stephen was saying exactly the opposite. No matter what you throw into the black hole, in the end you get out exactly the same thing.
In Susskind's argument, a holographic projection into the black hole from the event horizon allows the same information to be in two places without violating the concept of cause and effect. However, the holographic projection bears the identical problem, but in terms of symmetry and asymmetry about information, not just whether or not information is disappearing. Using a film projector as an analogy for Susskind's holographic theory, this would mean that we could have a film playing through a projector and yet have a different image playing on the screen. This does not preserve the conservation of information. The reason why this is a problem is that according to the equivalence principle, the film is not supposed to notice any changes as it passes through the projector onto the screen. However, in this example, the symmetrical image found on the film in the projector is not found on the screen, and the asymmetrical image found on the screen is not found on the film in the projector. These are, in fact, two different films with two different histories, a subtle difference not captured by black hole complementarity. Black hole complementarity can account for why information doesn't disappear in the future, but it cannot account for the subtle differences between the relative history of the information outside the black hole as distinguishable from the relative history of the information inside the black hole. To do this, you would need to account for CP violations and how they are related to gravity in a time-reversible manner, which flies in the face of current physics theories, requiring a complete unified field theory, which neither Hawking nor Susskind answer regarding the information paradox. Until this issue is resolved, physics is dead in the water as far as a complete theory of everything is concerned.
This is the Susskind-Hawking paradox. Information isn't disappearing, it's changing histories over time. The information paradox is back stronger than ever before, but this time it has teeth. Symmetry can change into other symmetrical forms. Asymmetry can change into other asymmetrical forms, but symmetry and asymmetry cannot merge into being the same thing without introducing something into the system. In our case, that would be a new physics. As it stands, supersymmetry and string theory are on shaky ground. The potential for Existics to surpass these great theories, as a working theory of everything, is at hand.